second difference. So the first difference was not constant, so I had to keep going and move on to the second difference. Because the second difference turned out to be constant, then I can state that it's a quadratic function, okay? So second difference are equal, so the relation is quadratic. We can do the same thing for second table. What can you, what do you have? 16, 24, 36. It's not constant. I have to move to the second difference. If I do the second difference, what do I get? Yeah? 8. And 12. So you see also the second difference is not constant. So in this case, it is not linear and it's not quadratic. Now what is it? We don't know yet. Okay, we don't know, we can't tell. I don't have enough information to assume that it's cubic or it's whatever, right? So for now, we're gonna just say it's not quadratic because the second difference is not constant. Because the question is asking, are they quadratic? Okay, always remember to read the question and answer what the question is asking you. Okay? These are review from grade 11, by the way, right? So these should not be new to you guys. If I look at the second, if I look at the graphs, which graph is quadratic?
C.
C. Yeah. So this is a quadratic, and I know that because it's a parabola shape. Right? This is not quadratic, it's linear. And then if you look at the equation, the first one is quadratic, and I know that because of the degree 2. And this is not quadratic, it's linear. That's a degree 1. Okay, this is the easy part, no? So often formulas representing real-world situations contain 3 variables, the dependent variable and 2 independent variables. So for example, in the formula for the volume of a cylinder, we have volume is equal to pi r squared h. Okay? So if you're going to look at these, this formula, can you tell me which one is the dependent and which ones are the independent?
Independent is the V.
The independent is the V?
Sorry, yeah. Dependent.
The dependent is the V because the V depends on the height and the radius, right? So the volume is going to always depend on what radius do you have and what height do you have, okay? So the volume is the dependent variable. While the radius and the height are independent, right? Now, if I'm going to look at this, and because I have too many variables, I can't say if this is quadratic or not. It's quadratic with respect to one, but linear with respect to the other, right? Because I have too many variables. If we look at the other equation, so if let's say if I had the other equation, which is 2x squared plus 7, there's only one dependent and one independent, right? So that for sure I know that it's going to be quadratic because my independent is to the power of 2, right? But if I'm looking at this, I have too many independent to be able to tell if it's quadratic or not. So I need to always set one of them to be constant and then state if it's quadratic or not. Which means, let's look at that example. To determine the relationship between the dependent variable and one of the independent variable, you're going to have to set the other independent variable to some constant value. You can't do your studies with too many unknowns. That's in this case 3 unknowns. Okay? You always have to set something constant. Okay? So let's say you're looking at the volume of the cylinder, right? You can't have the volume to be a variable, the radius to be a variable, and the height to be a variable. That's way too many variables. Okay? So you're going to have to just set one of the h or the radius as constant. So I want to look at the volume of the cylinders with a radius of 10. And then you can change your height. Right? Or you're going to look at the volume of these cylinders with a height of 10. And you can change the radius. And you can compare them. Okay? So you always have to set one of the independent variable to some constant value. We're going to look at an example. You can rearrange the equation to solve for the dependent variable. And determine if the relation is quadratic or linear or whatever it is. But for now, we're looking at quadratic and linear. Oh, it says or some other linear relation. Okay, so read that question, please. What do you guys think? So how many variables do I have here? 3 variables, which are? Distance, acceleration, and time. What are my dependent and my independent variables?
The dependent is D.
The dependent is D, and it depends on
On the time and
time and acceleration. Perfect. Now, so this is asking you to investigate the relationship between D and A when T is 2 seconds. So in this case, they gave you a constant value for T, right? So all in 2 for t, you have to rearrange your equation or like simplify it, okay? So that would give me d equals to 2a, right? Because I have 2 squared, that's 4. 4 times a half, that's 2. Okay? So if I'm looking at d equals 2a, can you explain to me, can you tell me if this is a linear or quadratic equation or relation? It's linear, right? Because you see here, now your exponent on the a is 1. Okay? So I can say that the relation between distance and acceleration is linear. So do you understand what I was just saying above with the volume equals pi r squared h? So you set one of the variables to a constant. In this case, they told you that the constant is t and it's equal to 2. Now what happened, or investigate the relationship between d and t when a is equal to 2 meter per second squared.
So what the
Plug 2 for a, yeah. So d is equal to a half a t squared. I'm going to replace a with 2. And then half times 2, that's 1. So d is equal to t squared. Okay? So what happened here, if I look at this, the relationship between the distance and time is a quadratic relationship because I have that square on the t. Okay? Are we good with that? Now, as I said, not all relations are linear. Some relations are quadratic, some relations are something else, right? So we have to be careful of what the question number 1 is asking us, but at the same time we have to look at our data. When we graph our data, we have to look at them, see if they're gonna be linear, if they look like they're linear, if they look like they're exponential, if they look like they're quadratic, how do they fit? So we can use what we call the curve of best fit or what we call quadratic regression. Okay? So we can use quadratic regression to model data that appear to lie along a parabolic curve and produce a curve of best fit. Now in this case, it's not a line of best fit, right? So you have to be careful, okay? Because when I ask you to find a line of best fit, what am I looking for? A straight line. When I ask you to find a curve of best fit, what am I asking for? Curve. Okay? So you have to read the question carefully. Okay? Even if you don't think the line is the best option, and I asked you for a line of best fit, that's what I want, right? Does that make sense? Hint, hint. That means read carefully the question. All right. A fountain of sparks from a Canada rocket follows an arc in the air. This table shows the height of the spark at various horizontal distance from the launching point. So I have the distance in meter and the height in meter. Use a graphing technology to determine the equation of the parabola of best fit. So in this case, they specify they want an equation of the parabola of best fit. So guess what? You're not going to do a linear because the question is saying parabola, right? All right. Now, what goes on the x, what goes on the y? Distance is on the x, and then the height is on the y. Perfect. Because it'll also make a difference if what you pick for x and y, right? You don't want to switch your independent and your dependent. Okay? So, what we're going to do here, so we're going to open Excel, and we're going to plot these points. Values that you see. So 5, is it going up by 5?
Yeah.
10, 15, stop at 30. I don't know what's going on here. 5. Okay.
And then for values 43,
43.
75,
75,
97,
97,
108,
108,
109,
109,
and then 100.
100.
Yeah.
All right. So, like exactly what we did with the linear, what we're going to do, we're going to highlight this. We're going to highlight the points. We're going to go to insert, and then we're going to go to the scatter plot and the first one. I don't want you to do this one. I don't want you to do this one. You always have to pick the first one. Okay? Now, with this format, you're going to have to add the axis. So you're going to press on the plus. You're going to add axis type. What do you think should go on the y-axis? What is it? Distance in meter. Make sure you always, the height on the y. Yeah, on the y it's height. Make sure that you always include your units. So you're going to include your units in bracket after your axis type. What would be the x-axis? Distance, again in meters. Okay? What would be a good title for this? The height of, yeah, of a Canada Day rocket. All right, so we graphed it. The points look nice. It looks like a parabola to you, right? So we included the axis title. Now what we have to do, we have to include the curve of best fit or the parabola of best fit. So can I have your attention here? So on your polynomial. It's going to be a polynomial with a degree 2. Okay? So make sure that you're picking a polynomial with a degree 2. And then you're going to display equation and display r squared on the chart. Okay? You see that when I display the equation on the chart, it turns out to be a quadratic one, which is, that's what I'm looking for. I'm looking for a quadratic equation. Because in the question right here, it says they want a parabola of best fit. Parabola means quadratic. And quadratic is a type of polynomial function. Okay? So it's a polynomial with a degree 2. Right? So you always have to read your question and see what your question is asking you to find. Alright? It's polynomial, so it does. It's P-O-L-Y and O-M-I-A-L. And O-M-I-A-L. Alright, now what we're going to have to do, we're going to have to snip it and then copy it to our Word doc. Are we okay with this? I'm hoping it's a yes. All right. So I'm just showing you what you're going to be doing on the quiz basis, on the assignment, right? So you're going to bring it here, and then you're going to paste it, and then this is going to be your graph. You have to check the insert equation on, so when you do this, you see the display equation on chart and display r squared? Yeah? You get that?
Yeah, my whole thing slows down.
Okay, now if you look at the r squared, what can you tell me about the r squared? What did I say about the r squared? It's 1. It's perfect. It's a perfect fit, actually. Okay? Because that's the best you can have, is 1. It's 100% fit.
Actually, I don't know, what is that R?
That tells you how well your exponential, so not exponential, sorry, how well the line of best fit is fitting your points.
Oh,
Okay? You learn that if you take data management, they teach you all about it. Okay? All right. Now, we graphed it. Now, the next question is asking you to determine the maximum of the regression curve and what does it represent. Where is the maximum of that curve? Between 20 and 25, right? It's going to be somewhere between 20 and 25, okay? So, a way that you can do this to get the perfect answer is you actually take that equation and graph it in decimals. And that would give you exact point, right? But if you don't want to do that, you can estimate. It won't be an exact value, it will be an estimate. So the estimate is going to be, if I look at this, if I look at this, right, these points, so basically my maximum is going to be somewhere here. Okay? It's between 20 and 25. 20 and 25, was it? Yeah. Right? So it's it's about 22.5. That's where my maximum is going to occur, maybe around 23. Okay, so what I'm going to do for you guys is we're gonna look at the graph and then we're gonna estimate and we're gonna say it's about 22.5 or 23. Let's put it as 23. Okay, because you see it's closer to the 25 than it is to the 20. Okay, and then we're gonna take that 23, and then what do I do with it to find the maximum? Plug it in to the equation. Okay, I take the 23, I plug it into my equation for x and find the height. Okay, so what was the equation again? Negative 0.2064 x squared. Makes sense that it's a negative because it's opening downward. So what I'm going to do is I'm going to plug in 23 for x. And the answer should be, can you guys find the answer for me? It's about 110.
Alright, can you show me what you're around here?
Sorry?
Alright, please don't talk about it. I don't know what's going on.
You know why? Because you are thinking, okay, when you go to this, highlight this. No. Yes, but I don't want these lights. You don't want. How did you do it? Okay, so press on one. Now, right click. And actually. Good? Alright. Okay, so what do you get here? 110?
Yeah.
And it makes sense because it's between 108 and 109. Okay? So the maximum, it tells that the firework reaches a maximum of 110 meter, right? At a horizontal distance of 23 meter, right? Because it's 23 for the x, that's a horizontal distance, and 110 meter for the y, which is the height. Now, if I'm going to take this equation and put it in decimals, I should be getting almost the same answer. Now, it could be like 22.9 or 28. It could be like a little bit different, but it's around that 23. Remember, we're estimating here, right? So what I'm going to do here, when you're done copying this,
What's that second word?
Tell. Sorry, I sometimes write So I'm going to go to decimals. 0.064 x squared plus 99193x.
This one's not easy.
So if I look at this equation, this is where my maximum is. And you see it's at 23.012 and 109.998. So that's a good